Welcome to Lesson 4 in Applied Evidence-Based Medicine in Integrative Health and Medicine, PIHM 7442. In today's lesson, we will be evaluating the literature, specifically systematic reviews and meta-analysis. The objectives are to describe the design characteristics, differences, strengths, limitations, and clinical usefulness of a systematic review and meta-analysis, to describe and interpret heterogeneity, funnel plots, and forest plots, and to list questions to consider for critique of a systematic review and a meta-analysis. Hopefully this is again a review for you because I know you just had some of this information. So this diagram shows us the different types of review there are, and you can see here that in all the reviews include also narrative reviews, systematic reviews, meta-analysis, and within the meta-analysis, an analysis that is specific to patient data and includes individual patient data. So let's examine this a little bit further. What makes a review systematic? Systematic reviews are based on a clearly formulated question. They identify relevant studies, they appraise the quality of those studies, and they summarize evidence by use of explicit methodology. And the authors provide comments based on evidence gathered. So again, a systematic review makes it such because there is definitive methodology involved in inclusion of the articles. When we get into data synthesis or a quantitative type of analysis, we are considering a meta-analysis. And a meta-analysis can be used in addition to qualitative synthesis when combining or pooling results from more than one study. The advantage of a meta-analysis is that it provides a numerical estimate of the treatment effect in the form of a risk ratio, odds ratio, number needed to treat, or a mean difference. And the disadvantage of this type of analysis is that the numeric estimate can be misleading if trials are combined or pooled inappropriately. And then another complication of a meta-analysis is often with the terminology. People misuse the term systematic review and meta-analysis, oftentimes using these interchangeably, which is not correct. A systematic review and a meta-analysis are not the same. So what is a meta-analysis? A meta-analysis is a way to calculate an average. It estimates an average or a common effect among different studies. It also improves the precision of an estimate by using all available data. The Venn diagram shows you that you can have a systematic review with or without a meta-analysis. And you can have a meta-analysis that are not part of systematic reviews. Someone could easily find a few studies that support their performed conclusion and calculate a result with no attempt to be systematic. These types of meta-analysis are very biased and should not be confused or referred to as being systematic in nature. Remember, a meta-analysis is a statistical method for combining results. And again, meta-analysis may be part of a systematic review. Systematic reviews may or may not include meta-analysis. So again, just to reiterate, a meta-analysis is a statistical method by which you are combining results from several studies. So again, hopefully this is a review, but a meta-analysis increases the power by combining results from individual studies. It combines the effects. So when we talk about results or effects, we're talking about the outcome in which those studies measured, such as the odds ratio, risk ratio, or the difference. The meta-analysis would come up with an average or common effect from multiple studies within the same population, interventions, and outcomes. It improves the precision of an estimate by using all available data, resulting in a weighted mean. So let's look at an example of a systematic review. We can see here in this example, which was published in Circulation in 2004, accumulated evidence on fish consumption and coronary heart disease mortality, that authors state explicitly the inclusion criteria for their studies. All relevant observational studies were identified by searching Medline and Embase from 1966 through September 2003. Search terms included fish, seafood, omega-3 fatty acids, etc. The search was restricted to studies using prospective cohort study designs and published in English language journals. So again, a systematic review will provide you details with how the articles were chosen to be included within that review. So this systematic review went on to do a meta-analysis, and we can see here the impact of fish oil consumption on cardiovascular diseases. We can see that the pooled estimate of the relative risk and the 95% confidence intervals of cardiovascular heart disease mortality for fish consumption of once per week versus less than 1 time per month. The squares indicate the adjusted risk ratio of each study, or relative risk. The size of the square is proportional to the percent weight of each study in the meta-analysis. The horizontal lines represent the 95% confidence intervals. Studies are ordered by year of publication, and pooled relative risk and 95% confidence intervals are indicated by the unshaded diamond at the bottom. The same study provides us with a systematic review and lists out the characteristics of the 13 included prospective cohorts in which the meta-analysis is based. So you can see here the source or the citation. You can see how many participants were in the study, the age, the percent of men versus women, the duration or follow-up, and the exposure assessment. A good systematic review will always have a chart or table that includes information about each individual study included in that review. So ideally, we'd like a meta-analysis performed within a systematic review. Within the set of a meta-analysis, the investigators will sometimes choose to go beyond the analysis of published studies, and they will contact authors of the primary studies for data on individual patients, and then combine the raw data. This is called an individual patient meta-analysis. So again, when authors decide to do a meta-analysis, they may just have data from the published article. But on the other hand, they may contact those authors of the published reviews and ask for the authors to share their raw data from each individual patient, and then combine the patient individual data from several studies into one meta-analysis. So one of the downfalls in a meta-analysis is whether or not combining results of individual studies is appropriate. And this involves an element of judgment. And the authors of systematic reviews and meta-analysis should discuss their reasoning for combining or not combining results across studies. Authors of systematic review and meta-analysis should also provide the reader enough information to judge whether or not combining results was reasonable. There are two types of heterogeneity, and the assessment of these sources of heterogeneity, such as clinical and statistical, are very important concepts. Clinical heterogeneity assesses whether the studies were reasonably similar with regards to population, intervention, and outcome, and also whether the combining of studies makes clinical sense at all. Statistical heterogeneity evaluates whether there are inconsistency in the results among or between the included studies. We'll look at the Q and the I squared statistic to determine statistical heterogeneity. Common sources of heterogeneity include clinical diversity between studies, such as patient characteristics, settings, interventions, or outcomes, conflicts of interest, and differences in study quality. So again, heterogeneity refers to differences between the outcomes of the studies. If most studies are similar to each other and show a similar result, you have low heterogeneity, and this increases the chance that the effect being measured is real. If results are from different studies that are vastly different, this suggests that each study is measuring something slightly different from the other studies. Heterogeneity can be due to a variety of things, including random chance, differences in patient population, differences in treatment, difference in patient follow-up, differences in assessing outcomes, differences in study design, differences in statistical tests, and differences in reporting results. Here's an example of clinical heterogeneity. This is from the meta-analysis by Neeson and colleagues from the New England Journal of Medicine that was looking at rosiglitazone and the cardiovascular mortality. Based on the introduction, we anticipate that the studies included in this meta-analysis include patients with type 2 diabetes who used rosiglitazone. However, when looking at the actual included populations, you can see that other populations, such as those with chronic psoriasis, Alzheimer's disease, or impaired glucose intolerance, were included. Inclusion of these very different populations with those with diabetes adds significant heterogeneity and could bias or lead to confusing or meaningless results. So this is another example why it's always important to look at your inclusion and exclusion criteria of individual studies. And oftentimes this may be found in a supplemental appendix, so make sure you always pull a supplemental appendix. So there are two parameters that we can look at to assess statistical heterogeneity: the Cochrane Q, or the chi-squared, and the I-squared parameter. The p-value with both of these shows that the probability that any difference between the studies is due to random chance alone. We want to see a high p-value. This indicates low heterogeneity. Heterogeneity should be low in order to combine individual study results into a single overall estimate of treatment effect. In the case of a meta-analysis, the p-values should be high to ensure that combining study results is appropriate. In general, a p-value greater than 0.1 should be seen in order to statistically combine study results. Let's take a look. This is done on a recent meta-analysis on the comparative cardiovascular effects of thiazolidine-diones, a systematic review and meta-analysis of observational studies. And this was published in BMJ in 2011 by Loke. And we can see here that the overall effect, if we look at this figure 2 for meta-analysis of odds ratios for myocardial infarction with rosiglitazone versus pioglitazone. So we can see pioglitazone is represented by the left-hand side, and rosiglitazone is represented by your right-hand side. And if we look at the top, we see adjusted odds ratio. And if we go down right before the unadjusted odds ratio, we see that there's a test for heterogeneity. And we can see a chi-squared with a p-value of 0.28. So again, we want this p-value to be high. We want it above 0.1. And we can see that it is. The I-square is 16%, which we'll review in a moment, and that means it's a lower number, less than 25%. That means it's low heterogeneity. So that means that it is appropriate to combine these studies. And you can see the studies that were combined include Billick all the way through to the end through Xyliday, 2009. So again, the measures of heterogeneity for us to assess statistical heterogeneity include Cochrane's Q, or chi-squared, and the I-squared test. So the chi-square, we're going to assess the p-value. The null for this test is variability is due to chance. A high p-value indicates low heterogeneity, and it tells us whether heterogeneity exists. It's not a very precise test, but it does give us a good idea. The I-square is a little bit more precise, and it's reported as a percentage. 25% is considered low, 50% moderate, 75% high, and it tells us the degree of heterogeneity. So again, the chi-square test for heterogeneity, we're looking at a null if homogeneity exists between the sample, relative risk or odds as an estimate of the population. So if we look at the same study, but we look at the unadjusted odds ratio, we can see that the chi-square test results in a p-value of 0.03. And we can see that the I-squared is 46%, which indicates that there is heterogeneity. The I-square 46% indicates about a moderate degree of heterogeneity. When we are looking at results from a study, we always want to use adjusted estimates. We don't ever want to use unadjusted. Authors go to trouble to adjust their estimates based on covariates. So we should always be looking at adjusted estimates. So in this case, we would want to interpret this graph with the adjusted odds ratio, which leads to, if we can see the final test subtotal of adjusted odds ratio for myocardial infarction, pioglitazone versus rosiglitazone, we can see that it's higher with rosiglitazone. On average, that has 11% greater odds of having an MI when put on rosiglitazone compared to pioglitazone. Now, one quick way we can assess heterogeneity is whether or not the confidence intervals overlap. So this was an interesting review I read called Heterogeneity, the Issues of Apples, Oranges, and Fruit Pie. And basically what these articles this author is saying is that quickly you can visually look at a forest plot, you can see whether the confidence intervals overlap. That means that the point estimates of the studies are relatively the same. Whereas if the confidence intervals do not overlap, and in this picture you can see that's on the right-hand side, that means there's heterogeneity present. The point estimates don't all overlap or not all the same. We can see that on the right-hand side we have an I-square of 80%, which is very high. So again, statistical heterogeneity can be spotted by a simple visual inspection of the forest plot. These plots show each an individual study estimate represented by a square, and the confidence intervals represented by the horizontal lines extending from the square, the low and the highs. The size of the square represents the weighting of each study in the overall synthesis. When the confidence intervals overlap, heterogeneity is lower than when confidence intervals do not overlap. Viewing data on graphs helps to have an immediate understanding, but we need to formally assess the information and not depend on our visual impressions alone. So one thing authors can do regarding heterogeneity is they can use a fixed effect or random effects model when providing data in the forest plots. So a fixed effect assumes the size of the treatment effect is fixed. It's the same across all the studies, and that variation is due to chance. We can use a fixed effect, or authors should use a fixed effect model when heterogeneity is absent. Otherwise, we're seeing a random effect model, and this assumes that there's a different underlying effect for each study. It's generally more weight is given to smaller studies and wider confidence intervals. When we use this random effects, or we see it used when heterogeneity between the study results is present. So this should be a review for you. I do enjoy this article. I will post it for you. It's Interpreting and Understanding a Meta-Analysis Graphs, a Practical Guide, and it was published in Australian Family Physician. It's a little bit busy, but it walks you through a forest plot. And we can see there at the top you have a title, and as we go from left to right, you have a study, you have the intervention groups. You should be giving the number of persons, the total number in the group, and the number in the group with the outcome. You have a control group, you have an outcome effect measure. So here it's showing a relative risk. They're saying in parentheses fixed, that means they used a fixed model, not a random effects model. We have an influence of the studies on the analysis, so that's a weight in percentage. So we can see that the highest weighted study is study B. And then we have a relative risk, and this is the outcome measure for that individual study. It is combined below by the overall effect. And we can see that the diamond is the overall effect, and we can see that it does cross our line of no effect, which in this case is a 1 because we're looking at a relative risk. And if you, again, visually, we like to look at the numbers to be certain. So if we look at our relative risk for the overall effect, we see it's 0.87 with a 95% confidence interval of 0.41 to 1.87. So it goes through 1. Therefore, the intervention group and the control group are not different. We see our test for heterogeneity, the bottom left. And hopefully you will see a scale of treatment effect. Let's look at this a little bit more in detail, but again, just a review since you should have learned this information already. So, first thing you do when you read a forest plot, you want to make sure you understand what the line of no effect is, which is the vertical line of no effect. So in this case, again, we're looking at a relative risk, and we know that that's a how you calculate a relative risk is through division. So we know that the line of no effect is going to be a 1 rather than a 0. And we know that the trials are represented by the boxes, and as we had already said, the weight is assessed. The larger the box, the more weight was given to that trial. The horizontal lines represent the confidence intervals. And it's a 95% confidence interval. And we know it has an upper limit and a lower limit. The larger your confidence interval, the less precise the outcome is. So you should be able to see the more precise the confidence interval, the larger the weight to the box. The diamond is the pooled estimate of all the trials put together. And the size of the square, again, is proportional to the weight and the size of the study and leads to precision. So when we look at a table, forest plot, we want to know the title. So make sure you understand which way your plot goes, whether it's going to favor to the left or to the right of the line of no effect. So in this example, we can see that the self-management of oral anticoagulation, thromboembolic events versus events by self-adjustment. We can see also at the bottom there's a horizontal line. This is a scale measuring the treatment effect. And again, 1 representing our line of no effect in this example. But you can see that the graph is showing an odds ratio. And again, an odds ratio is a factor of division, a ratio. So the line of no effect is a 1. The vertical line, again, is the middle. This is the line of no effect. We can see that the weight is given to the study. Again, visually you can look at the boxes, but I highly recommend you go ahead and look at the numbers associated with that study. The data, and these are persons, so this is also, when you review a meta-analysis, this is where you can get the number of persons if you want to calculate a number needed to treat, or if you want to calculate any of the other measures. Of course, this would be an unadjusted value because you're not able to adjust for all the co-founders. The label above the graph tells you the statistics being used. So again, this is using a fixed method. The pooled analysis is given as a diamond shape where the widest bit of the middle is located and calculated the best guess point estimate. And the horizontal line width is the confidence interval. If the confidence interval crosses the line of no effect, this is equivalent to saying that we found no statistically significant difference in the effects of the two interventions. A little side note here, most persons find it much more useful to give your point estimate with the 95% confidence interval rather than just a p-value. From a point estimate with a 95% confidence interval, we can tell whether or not it's statistically significant, and we can also tell the precision of that data. So it's much more useful to a clinician if you give the estimate effect size with the confidence interval rather than just a p-value. So this is an example of the entire chart, and you can see the arrows here are what they call trending toward, that they would trend in that fashion. They're really not necessary, but you will see some forest plots that include the arrows with the trial sizes. But let's look at the total effect. We can see that the odds ratio is 0.45. Thrombotic events versus events by self-adjustment. So again, you can say that the odds for a thrombotic event with self-management are 55% less than with the control group. Remember, odds are not the same as risk. So I always like when you use the word odds in your description of an odds ratio. So it just reminds everyone that odds are different than risk. Of course, odds approximates risk when the event is rare. So here's an example of the meta-analysis I alluded to earlier, comparative cardiovascular events of thiazolidine-dione, systematic review and meta-analysis of observational studies by Loke. And what I want to show you here is the funnel plot with this study. The funnel plot is a way to assess publication bias. Each dot on this funnel plot represents a study with its outcome. So in a funnel plot, we're again trying to look at publication bias, whether or not all these studies should have been combined. And what we can see here is that we have one study that's pretty much at the bottom. As you can see, the standard error of the log is a little bit above 0.8. And we can try to figure out which study this is and why it was included. But here we see on the x-axis, we see the effect measure. And on the y-axis, we see the log of the standard error, which is the variance of the effect measure. The less variance, the closer the dot is to the top of the graph. So this one little dot near 0.8 has quite a bit of variance. And we can just assume it probably also has a lower number of persons in it compared to the other studies. So again, publication bias, the results of a meta-analysis may be biased when included studies have bias. They may also be biased because they don't often include all studies, because studies with positive results tend to get published. So again, a funnel plot is an easy way to determine graphically if there is any publication bias. So again, studies can have different methodology. We want to make sure we assess, or the authors have addressed, differences in any internal and external validity. We know that less rigorous studies can overestimate outcomes. And we know that when we would combine studies with similar methodology, we want to combine RCTs with RCTs and observational studies with observational studies. You do not want to combine both RCTs and observational studies together in one meta-analysis. So again, this is the example of meta-analysis of the odds ratio of myocardial infarction with rosiglitazone versus pioglitazone. And we can see the adjusted odds ratio. We see that, again, that it has low heterogeneity by an I-squared of 16%. We can see an overall effect of 1.11 with a 95% confidence interval of 1.04 to 1.18, so 11% greater odds with rosiglitazone causing an MI compared to pioglitazone. We can see that the study with the less precision is the BILEC study. At the top there, we can assume, again, if you look at the weights, this is given the least amount of weight. It's not precise, so one would assume that this has a lower number of persons within the study. And again, a good meta-analysis and systematic review will provide you details of each individual study. And we can see here that indeed the BILEC study was published in 2010, and we can see that it has much less numbers of persons in it compared to the other studies. So what do we do about heterogeneity? Well, we want to make sure that random effects is used when appropriate, because remember, random effects assumes a different underlying effect for each study. We want to see subgroup analysis. Did the authors do an analysis with only parts of the studies or all the studies, and then also what kind of subgroup analysis was done? We may also see meta-regressions. This is just your standard regression, but it's looking at the heterogeneity by variation in study variables. And it's most often used with random effects models. And we also want to look for an explanation by the authors within the discussion section of that article. So I do want to say just a few things about epidemiologic measures. So these are your absolute risk reduction, relative risk reduction, number needed to treat, and odds ratios. And that you can calculate these if they're not given. Remember, these are number of persons and not events. And you would have to devise a 2x2 table. So in our study for the cabbage leaf, when we looked at this versus usual care and versus the topical NSAID group, we see that in the primary outcome measure, most of it is reported in numbers in a continuous scale on a visual analog scale. But we do notice that in a second paragraph under primary outcome measures, it says after 4 weeks, 8 patients in the CL cabbage group and 6 in the topical group and 4 in the usual care group showed a pain reduction equal or higher than the estimated minimal clinical difference. And then we look that up and we know that that is in the power calculation. Minimal clinical important difference, and in the power calculation they said it was 19.9 millimeters on a visual analog scale. So we can do our own little 2x2 table here. Of course, we only compare 2 groups, not 3, so I just chose the cabbage group and the topical group, and you can see when we do it, we have an average risk reduction of 7.4% and a number needed to treat of 13.5. I personally do not like the points, or because we can't treat half a person, so I would conventional rounding, just round that up to 14 for the number needed to treat of 14. So we would have to treat 14 patients before one would have a decrease in their visual analog pain scale of 19.9. A little note about clinical versus statistical differences. This was a study published in 2010 in Circulation, and it stated that intervention patients were less likely to have uncontrolled systolic blood pressure, odds ratio of 0.62, 95% confidence interval of 0.5 to 0.78, and were more likely to be adherent than control group patients at 6 months. But when we further look at the results, and if you look here at your results, we're looking at the group that says systolic blood pressure, millimeters of mercury, mean, and then parentheses SE, standard error, parentheses. So this is at 6 months, and it says at 6 months, intervention patients had significantly lower systolic blood pressure, 148.9 versus 151.1. P-value equals 0.008. So I ask you, even though that is highly statistically significant, is that clinically significant? You have a less than 2 millimeter change in blood pressure between the intervention and control group. So please be careful when you're reading through the articles that you keep in mind what is clinically significant and statistically significant. Go beyond the abstract. I was very disappointed to read this one study that was just published in the Journal of American Geriatric Society in 2018, just this last month. And it's a group at Kaiser at Washington State. And they're looking at the cumulative antidepressant use and risk of dementia in prospective cohort study. So what we do is we look at the abstract, and I'm going to read from the abstract, and it says individual antidepressant classes were not associated with difference in dementia risk, although paroxetine use was associated with a higher risk of dementia for all of the total standard daily dose categories compared to no use. And then it lists us some of the total daily dose categories and their 95% confidence intervals and hazard ratios. Well, let's just look at that a little bit closer. So the results say that in the total standardized daily dose, from 0 to 90, a hazard ratio was 1.69, and 95% confidence interval was 1.18 to 2.42. Well, that makes sense. Let's look at the next one, though. It says a total standardized daily dose of 91 to 365, hazard ratio of 1.40, 95% confidence interval of 0.88 to 2.23. Well, wait a minute. That is not statistically different, right? Our hazard ratio and our 95% confidence interval includes 1, so that we know that the intervention group and the treatment group are not different. And you can see the same thing when we look at greater than or equal to 1,095 total standard daily doses. So again, it was inappropriate for those authors to state in the abstract that paroxetine use was associated with a higher risk of dementia for all total standard daily dose categories. So lastly, I just want to review some questions to consider when critiquing a systematic review. You want to make sure that there's an important clinical question being answered with that review, and that a thorough search was done of the appropriate databases. So oftentimes we'll see Medline use, we'll see Embase, which is from Europe. But we may want to also make sure that some gray literature is searched. Gray literature, again, of those studies in which haven't been published. A great source of gray literature is clinicaltrials.gov. You will have results on clinicaltrials.gov, so you can certainly use that. You can also use your FDA approval information. That information is considered gray literature. Number 3, was the methodological quality assessed and the trials weighted accordingly? So how were the trials rated within this systematic review? How sensitive are the results? Was a sensitivity analysis performed? And then have the numerical results been interpreted with common sense? So that's also very important. You will see some authors not exactly interpret results appropriately. And then when you critique a meta-analysis, in addition to the questions about a systematic review, you want to know how heterogeneity was explained. Were the results represented appropriately? Was publication bias present? And are the results applicable to your population? So in conclusion, a meta-analysis with a systematic review can be a powerful tool to combine results from studies with similar design and patient populations. And critical review of methods, potential heterogeneity and biases are required to appropriately apply the results.